Welcome to StarTalk Live at the Beacon Theater, New York City. Tonight, we're going to discuss something that will change the world. The world is already changing right now. It will change it even more in ways yet to be plumbed, even by some of the most brilliant minds in the world. We're going to talk about quantum computing and all the ways that it will impact how we live, how we work, and how we play. All the ways that that will collide with our culture. And while I have some expertise in that, nothing that could justify an entire evening here, we combed the universe to see who has the expertise in quantum computing, quantum physics, and all that go with it. And we didn't have to look very far. Up the street at City College of New York, Professor Michio Kaku. You're a theoretical physicist, best-selling author, futurist, and his most recent book is called Quantum Supremacy: How the Quantum Revolution Will Change Everything. Came out just a few months ago, and it was a New York Times bestseller. And there's another empty seat here. We have a special guest. An award-winning actress and comedian, the star, as far as I can tell, she was the only one in the movie called Girls Trip. Give a warm New York welcome for Tiffany Haddish. Tiffany, oh my gosh. So all right, let's do this. We're going to talk about waves of technology as is impacted civilization. Now, Michio, when I think of waves of technology or advances, we all think of the Industrial Revolution as a big, good example where society was different before it compared to after. So I didn't know that you've numbered revolutions. What are we in today relative to back then?
Yeah, we're entering the fourth great industrial revolution. You know, throughout human history, we lived in poverty and disease. The average life expectancy was 30 years of age for most of human existence. Life was a bitch. But then something happened.
How did he say bitch? Was he good? How did he say?
I like the way he said it. It kind of turned me on. I was like, who are you talking to?
And that's a scientific term, right?
Yeah, scientific term.
But 300 years ago, something happened. We physicists worked out steam power, thermodynamics, which gave us the automobile, which gave us the train, gave us sewing factories, the Industrial Revolution. Then we physicists worked out electricity and magnetism. That gave us the light bulb. It gave us generators. It gave us power plants. Third, we physicists worked out the transistor. And that gave us the computer revolution. And now we are entering the fourth great era of scientific innovation and wealth generation: artificial intelligence and quantum computers.
All right, well, we got to start like square one. Remind us all about quantum physics. What is it? Many different communities have co-opted quantum speak. I don't know why, because I'm pretty sure they haven't ever had a class in quantum physics.
You're talking about the entire James Bond franchise, right?
I don't know, whole branches of society have done this. So just catch us up on quantum physics right here.
Well, the common sense world around us that we live and play with is Newtonian mechanics. Large objects that bump against other large objects, planets, meteors, comets, rocks, cannonballs, all governed by Newtonian mechanics. But at the tiny microscopic scale, a new kind of physics emerges: quantum physics. The physics that makes rocks and plastics and materials and flesh and blood all different. The thing that makes the world go round is quantum physics. And now we want to use that for computers. Now, a transistor basically has two states. The transistor can be on or it can be off. Two states for a transistor. However, once you go to a quantum transistor, then it can not only be up or down, but anything in between. And how many more states are there in between up and down? Infinite. Meaning that in principle, a computer that uses atoms to calculate is infinitely more powerful than an ordinary computer. That's why all the governments of the world, scientific laboratories are rushing to see who can create the first operational quantum computer that'll change everything.
I need a notebook and a pen.
Oh no, I was going to use this, but
No, I need this.
Oh, okay.
Because I need to know, what does Pluto-Maternus mean?
Well, we're talking about Newtonian physics,
Newtonian?
the
Yeah.
world of common sense, the world of cannonballs,
You said
planets,
common
comets.
sense?
Common sense
We
is
don't got that here. Come on now, common sense.
no common sense, not this side of the ocean.
No.
the common sense world is Newtonian mechanics, discovered 300 years ago by the great Isaac Newton. But now we're penetrating deeper into the nature of atoms, which are governed by a totally different kind of mechanics, quantum mechanics.
So here's the thing. So if quantum computing can be infinitely faster, more powerful than ordinary computing, which otherwise just has two states.
Two states.
Where do you see the first wave of this new phenomenon touching our lives? Where?
Realize that Silicon Valley will eventually become a rust belt of obsolete technologies, just like the abacus, because of the fact that we're going away from the traditional transistor. A transistor's smallest component may be 50 atoms across. That's huge on the atomic scale. 50 atoms across is the smallest transistor that we can make. We want to make a computer out of one atom. That's an atomic computer, a computer with enormous power that could change world history in the same way that the transistor, the same way that the Industrial Revolution changed everything.
We're on the precipice of this right now, you're saying.
Right now, we have created the first quantum computers just about 2 years ago. That's why it's called quantum supremacy.
What?
We're now talking about computers.
That's the name of your book, Quantum Supremacy. This sounds like you're ready for a fight.
We about to be fighting robots?
No fighting robots.
We just gonna be obedient to them?
No.
Maybe we should focus on quantum equality first. Just feels maybe like a kinder way of approaching the problem.
Yeah, how about that? Michio. Quantum equality, how about that?
No, we're way past equality.
What?
We're about 1 million times past equality.
Oh, you're a Republican. I get it. Okay, yeah. I get it. We've
No
dealt
comment.
with that.
Wait. So, since so many of us in so many fields use computing, quantum computing infused in all these fields would transform them all, I presume, provided they have questions that require this kind of extra computing power.
That's right. We're talking about computer power millions of times greater than what you can get from an ordinary transistor, which is either off or on, off or on. We're talking about millions of times more states than computer power in a quantum computer, which is going to revolutionize medicine, energy, space travel, transportation, you name it. Everything is going to be overturned in the same way that the transistor overturned everything after the war.
Right now, if I were to look out there, is there anything touched by quantum computing? Not yet. It's not ready yet. It's not ready for prime time. When will it be? Like next week? When? This sounds like...
Are you still taking investors? That's what we want to know. Like, yeah. Like, let's get in. Yeah. I missed out on the Bitcoin.
We've made the first quantum computers just a few years ago that on specific tasks are millions of times more powerful than a regular computer. Now the nations of the world, China, the United States, Germany, the European Union, all these countries are racing to see who can top that, to make a quantum computer that is general for all kinds of problems, not just one specific problem.
Give me an example of a task greatly improved by quantum computing. Because I don't know anyone here who's saying, my computer is too slow. Unless you have a slow internet, no one's really complaining. I remember in the old days, computers were slow. That's not a complaint today. So it's not a complaint, and you want to make my computer infinitely faster. So I don't know what I would do with that infinite extra speed.
What you can do with it is solve the secret of life. Solve the secret of energy.
Lazy. You're lazy, Neil. You ever heard about using it to solve the secret of life?
What is the secret of life?
He doesn't know it. He's going to solve it. That's what I'm saying.
Is it a secret or is it a problem? You
interesting.
solve problems.
Oh.
You reveal secrets.
Oh.
These quantum computers are so powerful that for chemistry, you don't need chemists anymore. We're talking about quantum chemistry done by a computer. Biology, you don't need doctors anymore to create new drugs. The computer will find new drugs. Energy, the computer will find new sources of energy. We're talking about a new industrial medical revolution right before our eyes as we make the transition from transistors to atoms.
All right, so we call this a bit. You said transistor, but a more primitive understanding of that is a bit. It's either 1 or 0.
That's right.
Right? We live in a binary computing universe. And now you have a quantum bit, which you guys have abbreviated to qubit.
That's right.
That's cute. I like that.
Quantum means how many, right?
Explain quantum, just the word.
When you look at energy, we think of energy as being continuous, smooth, and uninterrupted. Quantum means you chop it up, that there are pieces of the quantum. And these pieces of the quantum of energy are called photons. All the universe is based on particles, nothing continuous. So the world of continuous energy has been replaced by quantum physics, the physics of particles of energy that interact with other particles of energy.
So like when somebody come through and mess up your vibe, they just did a quantum leap into your existence.
Well, yeah, a quantum leap is now part of the vocabulary.
But it was a great show.
Give him a Peacock account, I'll give you my streaming password. We'll catch you.
Yeah.
Okay.
Explain to me sort of parallel computing, because you can calculate two things simultaneously, two different things to help you get one answer. And what does quantum computing do to that problem?
Well, let's put a mouse in a maze. If you put a mouse in a maze, a digital computer calculates each trajectory and says, do I turn left or do I turn right? Left or right? And how many waves does it take to go from point A to point B? There are potentially millions of paths for a mouse to go from one point to another point. That's a digital computer. One by one, it calculates each path as you go from A to B.
So this path, that's not the exit. This path is not the exit. And this is going one by one until it lands on the exit.
Right.
Okay, so now what?
That's today. A quantum computer scans all possible paths simultaneously. Instantly, all possible paths are scanned. This is incredible. This is fantastic. This defies common sense. But this is the reality of Mother Nature. This is why Mother Nature is a quantum computer. When you go outside and you see the forest, the leaves, the trees, you say to yourself, how many chemical processes are there? Thousands of chemical processes happening. How can Mother Nature do that? Because it's all quantum.
All right, so Michio, deep within quantum physics, there's this remnant of many decades past, maybe it's still with some quantum physicists, where they speak of many worlds, interpretation of phenomena that are happening but you can't see them, so maybe there's another universe in which that's taking place. Does any of this quantum computing touch on the idea that we are bringing together parallel universes?
Yeah, in fact, the whole power of quantum computers is because it computes in the multiverse. Hollywood and Marvel Comics discovered this only recently. If you look at
It
Marvel
feels like
comics,
forever ago.
It does. It does.
Spider-Man exists in the multiverse. All the Spider-Man movies are now in the multiverse, where Spider-Man exists in multiple states of reality. Look at the Oscars. The Oscars, the big winner last year was Everything, Everywhere, All at Once. That's how an electron views reality. Everything happening all at once is how an electron sees things. So when I look at myself in a mirror and I see myself, I say to myself, that's not really me.
You say that to yourself.
I say that to myself. I say, that's
say
an
it every
average.
day.
Wait.
Every day
That's
I
an
say that.
average.
That's not me.
There's a word for that.
Besides mental illness.
There's a word for that. Okay.
But this is the quantum
He's doing
world.
science, Neil.
He's doing science.
He's doing science.
We exist in multiple states. So when I see myself in a mirror, I say to myself, I'm looking at an average. An average because the real me is hovering over all different possible states. Some of these states are on Mars, on Jupiter. Most of the states are right there in my living room. But this is how I think. And that's how quantum physicists think. We calculate the probabilities of living in a multiverse of universes.
Chapter 7 is on mushrooms. I'm just.
I feel like you're describing me when I'm on my cycle, because like my body is here, but my mind be in another dimension demolishing things, and then my spirit be trying to make it okay to be here. It's crazy. I have a lot going on.
Well, remember when your mother used to say to you, you cannot be two places at the same time?
That's not true.
She was wrong.
She was.
You can be many places at the same time.
I have been lots
That's
of places.
called quantum mechanics.
That's when I'm finna start saying, look, I'm in my quantum mechanics right now, please.
Okay, give her space while
I'm
she.
quantum mechanicing.
I mean, so you're telling me you get up in the morning before you brush your teeth, you look in the mirror, you say, I'm not here, I'm average, and my mom was wrong, and you don't think this is a cry for help?
That's right.
Okay.
I look at myself as an average in the mirror because I exist in many, many parallel states. Some of these parallel states went out the door, went to school. There I am, watching myself. And I say to myself, this is reality because we exist in multiple universes. That is the power of quantum computers.
Chapter 8,
Quantum
LSD.
computers compute in multiple universes.
Wait. So I hear you. How does that relate to quantum computing?
That is the power of quantum computing because just like a mouse in a maze uses the Newtonian path, one path at a time, each joint with a certain probability of going left or right.
So the concept and the title of that award-winning movie, Everywhere, Everything, All
at once.
Right.
This was a wet dream for you, watching this movie.
That is how an electron views reality. Okay, we view reality as an average. We average over many electron states, and we call that...
I got this now. You were going in other dimensions, resonating with Tiffany here,
Yes.
about being an average you, but part of you was on Mars. The electron, whether or not it's on Mars, and whether or not it's on a parallel universe, it does exist in multiple states. Whatever those states are. I'm not going to stick it on Mars for the sake of putting it on Mars. It's got it in multiple states, and it realizes all of those states at once to find the answer. Am I correct?
That's right. And how do you know finally when you land on Mars or wherever, how do you know you're on Mars? Because you make a measurement. When you make a measurement, that's when all the waves of electrons collapses to where you are. Now, John von Neumann, a great mathematician, one of the greatest of the last century, was asked, how can you get your head around that? How can we exist in multiple states until you make a measurement? And then one of the great mathematicians of our time said, you just get used to it. This is called modern physics.
Okay.
Or marriage.
Okay.
One practical application of this is the atomic bomb. The atomic bomb was one of the first major applications of this theory, and it works. It changed world history. We're not talking science fiction. We're talking fundamental physics of the universe.
So Matt, I hear you have something coming up in the desert.
Yeah, 29 Palms, California, just outside Joshua Tree. We're doing an event called The 29 and Beyond. It's going to have stand-up comedy, podcasting, science, and stargazing. We've got headliners.
That sounds like a must.
Oh, yeah, absolutely. We got Bobcat Goldthwait, comedy legend.
Nice.
Reese Darby from Our Flag Means Death and Fly the Conchords. We got Natasha Leggero, Moshe Kasher. Then we got scientists. We got NASA people. We got stargazing from Skywatcher.
Whoa. Wait, so my invitation's in my inbox? Is that what you're saying?
Fingers crossed.
It sounds like it's the beginning of a great tradition.
I hope so, yeah. So if any of your listeners and viewers want to come to 29 and Beyond, that's where all the info is, and June 7th and 8th.
Dude, give it to me. Let's throw in some new vocabulary here. These computers can't just work in your hip pocket. The atomic state has to be sort of reduced to the least possible external energy influences on what it does.
Right.
And the only way to do that is to drop the temperature so it's not vibrating it's like get it so that the only thing happening is what the atom wants to do unto itself. And so you got to get this thing to nearly absolute zero.
That's right.
In the old day, I'm old enough to remember, computers used to be the size of rooms, and there was a whole other room just to cool the room that the computer was in. Not to absolute zero, but to keep it so that it doesn't burn out its own circuits. If this has to operate near absolute zero, then it's not just something that anybody has in any lab.
A quantum computer today looks like a chandelier. A gigantic chandelier with all sorts of cooling pipes. But you see, that's not the quantum computer. The TV cameraman got it wrong. The quantum computer is that little box at the bottom of the chandelier. Everything else are cooling pipes. Cooling pipes to bring it down near absolute zero, where there's no disturbance from vibrating electrons.
Got it. Vibration from the external temperature in which it might have been immersed.
That's right.
Okay, so now we've got this. You've described it to me. I can picture it. So now what is happening on this chip? You're saying it's solving everything all at once. I have a computer program. How about like the three-body problem? That's a famously intractable problem. I want to solve that. And it takes thousands of hours or whatever, and maybe the answer still isn't right. Can I just use that same program and just hand it to the quantum computer? And then out comes the answer fast?
I know, you're going to have to learn a whole new language of computer language.
That's what I was wondering. Okay, that's
a
what I
whole
was
new
wondering.
language, because of the fact that we're no longer dealing with certainties. We're now dealing with uncertainties. Uncertainty. This is called the Heisenberg uncertainty principle.
Wait, I want my answer to be certain.
Sorry about that.
So tell me about superposition of states. Is this, when we say that an electron can be not just up or down like a 1 or 0, but in any state, at any given moment, it's living in all of those states. Is that a fair way to say it?
That's right.
Like the cat, Schrodinger's cat. Catch us up on Schrodinger's cat.
Is that thing still alive?
No one has fed it in years.
You guys, oh man. Somebody get to that house.
Isn't it a superposition of being alive and dead?
What?
The most famous cat in all of science is called the Schrodinger.
Garfield?
It's Garfield. It's got to be Garfield. That guy eats so much lasagna and he's still alive. You're telling me that's not the most famous cat in all of science?
You take a box and you put a cat in a box with a gun.
What?
The gun is pointed at the cat.
Get help, man. Get help.
gun
Stop
in turn-
screaming in the mirror. Jeez, let's get this guy a
I want to
psychologist.
start dating scientists. Y'all freaky.
You asked the question. I'm giving you the answer.
No, it's just funny because you started up. I said, I look in the mirror and that's not me. And then
You got a cat in a box with a gun?
so we got to like take this one step at a time. Okay.
I love
a
it.
cat in a box
Sexy.
with a
Keep
gun.
going.
Okay, we're with you so far.
And the gun is connected to a trigger. And the question is the gun firing to kill the cat? In other words, is the cat dead or alive? Quantum mechanics says that before you open the box, the cat is both dead and alive simultaneously.
A superposition,
A superposition
of a dead and alive state.
of a wave of a dead cat plus the wave of a live cat. Okay? When you open the box, then the wave function collapses and the cat is alive. Or maybe the cat could be dead. This is all a question of probabilities. So in other words, is it possible to talk to dead people?
Yes.
In this way, it is possible under very rigid circumstances that you're not really fully dead or alive until you open the box and make a measurement.
Why can't I say you don't know if it's dead or alive?
Yeah, you
until
don't
open the
know
box?
until you open the box.
But that doesn't mean it is neither. I guess I'm not allowed in this universe to declare a truth inside of a box I have yet to open.
That's right. You are not allowed to say if the cat is dead or alive until you open the box.
Well, you got to do measurements, though. How long has that cat been in the box? Did you put food and water in that box? Is there somewhere for that cat to use the bathroom? Is it eating its own poop? Because then, that's it might make it. But if it's been 3 weeks, it ain't going to happen. That cat did it.
Michio, she's got a point. I'm thinking she's got a point.
What's the numbers on this? How much time is the cat in the box?
Now, of course, this cat is actually a representation of an atom or a neutron. And that neutron could be the trigger of an atomic bomb. This is how atomic bombs work.
Okay, so the cat is metaphor.
It's a metaphor for subatomic particles that set into motion the atomic bomb. So for people who don't believe in this theory, I just advise you to go to the Los Alamos testing range and test your theory when the bomb goes off.
Okay.
He's getting dark real fast here. Okay.
To be fair, Garfield's also a metaphor for Chernobyl. So this is how these things work.
Is that it?
It's how it works.
All right, so just put some more vocabulary in the house. Tell me about quantum entanglement, which has been a lot in the news lately.
Does this got something to do with Will and Jada?
You said Will and Jada?
Yeah, because she talked about the entanglement.
Oh, right.
Oh, yeah.
Yeah.
Is this about sex?
Okay, one at a time. Let me answer.
No, this all happens at once. Everything's at once. We can talk about quantum theory.
Put on your quantum brain and answer all these questions simultaneously.
Yeah, touche.
There is a Michio right now who's talking exclusively about Will and Jada somewhere in the universe. Scientifically, that's possible, right?
Yeah.
I'm not really here.
That's right.
You don't really want to be here. I think that's different.
Tell me about entanglement.
Okay, remember we talked about the fact that an electron could be spinning up or spinning down.
You didn't use the word spin. You just used your thumb. But spinning, it's a spin thing. Yeah.
While a quantum computer, the things can spin in any orientation. Not only that, but the two spins can interact with each other. That's called entanglement. And that should not exist in a Newtonian world. But in a quantum world, atoms talk to each other. Then the question is, how fast do they talk to each other? If you signal from one to the other, it turns out it goes faster than the speed of light. At that point, Einstein said, this is nonsense. You cannot go faster than the speed of light, therefore quantum mechanics must be wrong. Einstein put his reputation on the line and said that atoms cannot talk to each other faster than the speed of light. Well, Einstein was wrong. We've done the experiment. Information travels faster than the speed of light. But what's the catch? There's always a catch someplace. The catch is the information that goes faster than the speed of light is useless information. In other words, quantum mechanics has the last laugh. Einstein was right. You cannot go faster than the speed of light, but he was only partially right. It means that usable information cannot travel faster than the speed of light. But information that's raw, can it go faster than the speed of light? The answer is yes.
Gossip, bad
Gossip moves.
So on Star Trek, when you talk to headquarters, they talk via subspace communicators, right? That's how Captain Kirk talks to Earth Command, right? Well, there is no such thing. Because some people say, well, that's entanglement. Captain Kirk is entangled with the Earth. That's how he's able to speak faster than the speed of light to get orders from headquarters. Doesn't work. The information you get from entanglement is random, static information.
But Michio, it does work because it's Star Trek, just to be clear. They're just ahead of you by several centuries, that's all. So entangled particles are not actually communicating with each other. So in that sense, Einstein was right.
In that sense, he was right.
So even when Einstein was wrong, he was right.
That's right.
Yeah. Okay, so that's entanglement. Does that matter in a quantum computer?
Yeah, because it means that below the speed of light, atoms will indeed talk to each other, and that's how they exchange information. While in a digital computer, each transistor is separate. Transistors do not influence each other's mode of communication. In the quantum realm, there's a wave function that glues all these particles together, the electron wave.
So the wave function, let's just dig into that just for a moment. So we've all heard of the wave-particle duality. Anyone here has heard of the the wave-particle duality. So we can think of particles. We're taught electrons, protons, neutrons. Then you take quantum physics and you say, well, it's also a wave. But if you think of them as just particles, they cannot realistically interact other than through their charge. But if you think of them as a wave, then the wave interacts out here somewhere because it's not just localized where the particle is. And so is this the wave interactions that you're describing?
Yeah, here's how it works. Fundamentally, all subatomic particles are particles, not waves. But the probability of finding that particle at any given point is given by a wave. That sentence was worth several Nobel Prizes.
For something that could probably be, you get a Nobel Prize? I'm coming with some new ideas.
You put that in mathematical form, and that's how it works. In quantum mechanics, all particles, subatomic particles, are particles. But the probability of finding that particle at any given point is given by a wave.
All right, so Michio, you're no more powerful to manipulate anything than the precision of the tools you have at your disposal. If you're telling me what atoms are doing, what electrons are doing in a quantum computer, who's putting them there? Who's adjusting them? How is my program that I just wrote up influencing those particles?
Yeah, if they doing the wave, is a mascot running back and forth across the thing, getting them to do the wave like at a football game?
This is not a football game.
But they're atoms.
Looks like a football wave when they wave across the stands, right?
Mm-hmm.
Well, that's an example of particles, that is people, giving you a collective motion called the wave at a football stadium. So is that wave really a wave or is it a particle? It is a particle that bunches together to form a wave.
So who making that happen?
We are the particles making the wave.
Yeah, and the mascot is making the particles make the wave.
Oh, okay. So the mascot is the program setting the computer into motion.
And a guy got a Nobel Prize for this.
But wait, just to be clear, this wave, when we think of waves, we think of ocean waves and sound waves. But the wave in a stadium, nothing is moving.
Well, in the stadium, people jump up and down, up and down.
But nothing's going in the direction of the wave.
Yeah, but the same thing for sound waves. Sound waves do not necessarily have to go at the speed of sound. The vibration, when one atom hits the next atom, can go at the speed of sound.
Oh.
But each individual atom can be slower than the speed of sound.
Okay. Yeah, he got me there. That's a good one. So what you're saying, in a sound wave, I'm just vibrating these molecules right here, and they bump the next one, and they bump the next one. So when you hear something, you didn't hear any particles come out of my mouth. You experienced the energy transmitted through the medium before it reached your ear.
The energy and information goes at the speed of sound, but each atom did not.
Does not.
Each atom only went a very short distance and stopped.
Okay, so tell me again how all this gets maneuvered and manipulated to do its business at the bottom of the absolute zero system.
Yeah, when you see a picture of a quantum computer, it looks like a gigantic chandelier with hundreds of pipes. At the very bottom, there's a box. The box is where you have electrons dancing in either spin up, spin down, or spin sideways.
How do I control those electrons? I don't have tweezers to make it do what it's got to do. How does that happen?
You have to program it initially so that the electrons are in a certain formation because they're all coherent. They vibrate in unison.
Okay.
They talk to each other.
So there they go. So now take me to the next step.
You prepare them to vibrate in a certain way, and then you make a disturbance. You make a disturbance, and then the disturbance is a calculation. And you don't calculate on this wave. And that's how you can calculate numbers that are beyond what a digital computer can do.
So has this language, this computer language, been established for this purpose?
Well, the big companies, Google and IBM, they, on the web, you can actually play with a quantum computer. It's very primitive, only does a handful of qubits, but you can actually program a quantum computer on the internet tonight. They already are on the internet. Now, eventually we want to have qubits in the thousands and millions, but right now you can play with a quantum computer tonight, a quantum computer with maybe 10, 15 qubits.
So isn't that already quantum supremacy? We already got it going?
Well, we want an all-purpose device that'll work for any problem, and any problem that'll then outrace a regular computer. Okay. We're not there yet.
Is there a day when I'm going to buy a quantum computing iPhone and put it on my hip?
Yes, because your iPhone will then communicate with the web. On the web, there'll be a few acres worth of quantum computers that are just dedicated to doing quantum calculations. Now, why would people do this? The nations of the world are in a race. There is a race between China, the United States, Google, IBM, Russia, to see who can get the first quantum computer that could crack any known secret code.
How do you crack a code?
Put a girl on it that's nosy.
Normally, you crack a code by factoring numbers, like 15 is 3 times 5. Okay, it takes a computer to calculate that if the number is 100 digits long. Given a number that's 100 digits long, factorize it as a product of 2 integers. That takes several thousand years.
Of a computer that we have today.
Right.
Okay.
A quantum computer will do it like that.
So all of our encryption today will go obsolete overnight.
That's right. All your codes, all the codes that you faithfully put down in a notebook, knowing that it's safeguarding all your secrets, all your family jewels are there, right?
Well, Tiffany just covered up what she wrote. The quantum computer's not looking under her hand.
It can't see paper.
Paper.
No, can't do that yet. Maybe next year.
Wait a minute, so you telling me that my blockchain is going to be getting interrupted? It could be like all up in my Bitcoins?
That sounds painful, your blockchain up in your Bitcoins.
I know, right? I was using all the power of the bees.
The first country that attains a workable quantum computer can break into all the intelligence agencies of the world.
Okay, so let's bypass that for a moment.
What?
No, what I mean is, wait.
They don't have to start going back to paper.
I got this.
We got jobs, y'all. We got jobs.
Wait. No. If we know that in advance, then we find something else that a quantum computer can't do in the same way regular computers can't factor the primes or whatever that is. So put that in place. Okay, we're done there. What is next? And by the way, that's not so weird because we've already been through other security protocols in our lives that today you would laugh at.
Yeah, but this one hasn't been broken yet. Nobody knows the answer. If you could figure this out, the CIA is going to give you a phone call tomorrow.
Let me shut up because unless they trying to date me, I'm not giving them no information.
Exactly. You just let out the secret of how to get the information. Well, so let's assume we get past the encryption code issue.
Okay.
What are the next tasks to apply this awesome power of computing to? What is sitting right there, low-hanging fruit?
Cyber medicine. We're talking about curing cancer, curing Alzheimer's disease.
Right now we can't, and tomorrow we will, because
These diseases we conquer trial and error by making petri dishes, thousands of petri dishes, putting the chemical and the germ inside them, and simply crossing your fingers that one of these petri dishes will signal a cure for that disease. That's how we do it. That's how they did it during the Middle Ages. We still do it this way, trial and error. Well, now with the quantum computer, we can simulate the molecule. We're talking about chemistry without chemists.
So you will have full information of the atoms and molecules in the interaction of every petri dish, and you could do it for billions of petri dishes on the computer, and it'll pop out what the right remedy is for the disease
That's the goal.
you're trying to...
Take a look at photosynthesis. The world economy depends on photosynthesis. That's why we eat. That's why there's food, photosynthesis. But we still haven't been able to model photosynthesis in a computer because it's a quantum mechanical phenomenon. Light that grabs carbon dioxide turns into sugar. That is a quantum mechanical operation that we cannot model using Newtonian mechanics. So quantum computers can solve the problem of food. Take a look at fertilizer. Nitrogen exists in the air. You take nitrogen out of the air, make fertilizer out of it. It takes a huge, gigantic factory to do this. Gigantic, billions of dollars to make fertilizer out of the air. Quantum computers, we think, will do it like that. We're talking about a second revolution.
Wait.
How is a quantum computer going to take nitrogen out of the air and then disperse it in order to get into all the earth to grow food?
How's the computer going to do? What are you saying?
The computer does not take nitrogen from the air. It simply models how nitrogen can be taken out of the air, catalyzed by a catalyst to make fertilizer.
Why can't we do that right now?
Because
we don't know how to do it.
We don't know how to do it. Because, like I said, it's trial and error. Almost all chemistry and biology is done by trial and error.
Mostly error.
How is penicillin discovered? We discovered new penicillins the same way, by accident. So we're now talking about not by accident, but systematically creating fertilizer, creating new drugs, new therapies. Because that's how Mother Nature does it. Mother Nature does not do it by petri dishes. Mother Nature does it quantum mechanically.
In my field, we have fascinating computing challenges with the Big Bang and the early universe, and they're not so much atoms. When the universe expands and makes stars, there's a lot of things we have to track in the early universe. The energy, yes, the particles, but also when they make stars and how do they coalesce, and there's the gravity and the dark matter and the dark energy. So I'm just thinking I need a more powerful computer. I'm not creatively thinking what I could do if it was billions of times faster. Do you know in advance what challenges, cosmological or in physics, that could be?
The number one challenge is to explain the Big Bang itself. What happened before the Big Bang?
Now you're a pioneer of a string theory. What variant of string theory are you?
Well, the whole field itself.
Wow.
He the pioneer of the strings.
Excuse me. Okay.
Lex.
So string theory gives us access to conditions in space and time that ordinary physics does not enable, including the singularity that was the Big Bang. We don't really understand that. Why would quantum computing get us there?
Well, we think that before creation, the universe consisted of something like boiling water. Lots of little bubbles forming, colliding with other bubbles, popping in existence and out of existence. Boiling water, that's the early universe. But sometimes one bubble keeps on going, doesn't stop, bumps into other bubbles, keeps on growing to become the universe. So in other words, the universe itself, we think, came out of a bubble. And that bubble, in turn, comes from string theory. String theory predicts that at the beginning of time, there was quantum foam. Quantum foam, as we call it, tiny little bubbles like boiling water. Most of the time, they pop into existence and pop out of existence, never to be seen again. But one bubble just kept on going.
Why does quantum computing help you there?
Because we don't know how this happened. We want to be able to calculate the equations that'll take us from before Genesis to after Genesis. And that's what we need, quantum computers.
You have an understanding enough to be able to write the program that'll take us from before time to after time.
That's right. However, string theory is so complicated that no human has the ability to solve the equations. We have the equations. I wrote many of them myself.
You have the equations.
We have the equations, but...
Where do you keep them?
in my desk drawer.
You're like, yeah, you're not afraid of somebody taking them and figuring them out. So,
But you see, that's where we're stuck. We're stuck at the point where we have lots of solutions, but we don't know why one solution was singled out to give you the Big Bang. This is called the landscape problem. We have a landscape of possible universes. Why did this one universe become the universe that we see today? That's why we want to solve the equation. Now, no human is smart enough to solve these equations. I repeat, no human alive is smart enough to solve these equations.
Let me look at it.
Tiffany's got this one.
I don't know. I'm pretty good.
Wrapped up.
You'd be surprised.
But that's why I got interested in quantum computers. I think a quantum computer may crack the problem. A quantum computer may crack the problem as to which bubble created the Big Bang.
So then it'll help you focus in on that.
That's right.
All right, so can quantum computing help with space travel?
It may help us because space travel is limited by the speed of rockets. It takes 70,000 years just to reach the nearest star traveling with the Saturn V rocket. We can't explore the universe that way. We need another way to explore the universe.
And so how does quantum computing help that?
Well, Einstein came up with an idea in 1935. That is, why not bend space and time on itself to give you a wormhole?
The Quantum Leap TV show.
Wormholes. Okay, so the public is very well versed in wormholes. I mean, we've got it. Who's this guy right here? Doctor Strange.
Yeah, sure.
Okay.
Yep.
We got Rick and Morty.
Rick and Morty do it. Yep.
They both open up portals through the space-time continuum, except Rick does it with actual science, and Doctor Strange uses magic. You know, just to.
But then in the show Quantum Leap, because he was able to go into different, he leaped through a hole.
Through a hole.
Into different time periods.
Through a hole.
Doc Brown, you got to mention Doc Brown too.
Well, that's just a time machine.
And Doctor Who.
But I mean, he's going through some sort of portal.
And Interstellar, they found a wormhole to make their trip easier to their destination.
And what about Doctor Who?
Yeah, I guess so. Doctor Who. That's back when wormholes were still shown as water slides.
Dr. Zhivago, I think, goes through one, maybe.
But now you just step through when you're there. So how do I make a wormhole?
Well, first of all, if you watch the movie Interstellar, at the very, very end of the movie, Matthew McConaughey is floating. What is he floating in? He's floating in the fifth dimension of a tesseract. He's floating in string theory. The movie Interstellar ends on string theory. He ends in hyperspace, a dimension beyond the four dimension of Einstein.
You say that like, yeah, of course. Yeah, I knew that. We all knew that.
Could you explain Tenet to me? Because that one I can't wrap my head around.
I'm confused as hell.
What we really need is Christopher Nolan here.
Yeah, okay, yeah.
Who, by the way, he's a friend of StarTalk. We've had him on the show.
Is that right?
In the past,
Look
yes.
at that brag. Yeah. This guy created string theory, so that's nice, Neil, but come on.
So a wormhole is highly unstable, wanting to collapse upon itself. How do you keep open a wormhole?
Well, you're right. It takes positive energy, like a star, collection of stars, dead stars, to create the wormhole, which is a gateway between our four-dimensional space-time and another portion of space-time. And it was Einstein himself who introduced that idea in 1935. And then the question is, how do you keep it open? That requires negative energy. We haven't seen that before. It's a new form of matter, negative matter. But negative matter will stabilize the wormhole so that in principle you can go through it to another point in space and time.
Without it collapsing down on top of you.
Rather than collapsing down, in which case it would crush you in half. You don't want that to happen.
With half of you in one part of the universe and the other half in the other half of the universe.
That's right. That really would make your day.
All right. You just say negative matter like that's just a thing. But I've never seen it.
I've experienced
Negative
it.
matter would fall up rather than falling down. If negative matter existed, it would have fallen up billions of years ago. That's why we see no negative matter on the Earth today, because if it ever did have negative matter at the beginning of time, it would have fallen up billions of years ago.
Wait, what?
Wait. So I could dig in the soil And if a rock just flew up, then that was negative matter trapped for the history of the Earth.
It turns out that negative energy will also do this. It requires a lot of negative energy, but negative energy has been created in the laboratory. We've actually made minute quantities of negative energy, not matter, negative energy in the laboratory. If we can harvest large quantities of negative energy, then in principle, you may be able to build a time machine or a wormhole machine, in principle.
I didn't know we made negative energy.
Yeah, negative energy is done at the microscopic scale with nanoparticles. With nanoparticles, you can play with negative energy. It exists, and we play with it. But large quantities of it are required for a time machine.
Can I go through a wormhole and come out in another universe?
That's the theory. No one's ever done it, so we don't know for sure. But that's what the theory says, yes.
Okay, so if there's another universe, or many universes, and I can travel among them, how many other universes might there be in your quantum foam model?
Well, it depends on the star that created the wormhole. If it's an ordinary star that's very massive, like a dead star, a black hole, then you use what is called the Kerr metric. The Kerr metric then describes a dying star, and it's a one-way trip. You can go through it to go to a parallel universe, but you can't come back.
So you go through the black hole, through what is ostensibly a wormhole, and get you to another universe.
That's right.
This is a non-rotating black hole.
Right.
That right? Okay.
But you can't come back, okay?
All right.
Now, recently at Caltech, they discovered transversal wormholes, and that's the basis of the movie Interstellar, right, where you can go backwards and forward, but it requires negative matter and negative energy. Then you can go back and forth like what happens to Matthew McConaughey in the movie.
And the co-executive producer of that is a professor of physics named Kip Thorne, an expert on cosmology who surely helped write that storyline.
That it ends on Kip Thorne's theory. That's right.
So let me get back to your earlier comment that Mother Nature is a quantum computer. Did you say that?
In that sense, yes. You go outside, you see photosynthesis taking place, you see energy being converted into useful chemicals, you see life, you see all sorts of chemical processes happening, none of which can be duplicated by an ordinary computer. That's where quantum computers can come in.
And all of it is happening like it's just another day under the sun.
That's right. So in other words, we actually have quantum computers. They're called leaves, plants, vegetation. All of them are quantum mechanical. Why did you eat breakfast this morning? It was a byproduct of quantum computers. Why do we have a green revolution? The green revolution was a quantum revolution. That's why we had fertilized crops. And that's why we have a food shortage today, because we're running out of fertilizer. That's why we need quantum computers to come in to fill the gap. A second green revolution is a byproduct of the quantum revolution.
Wow. And that would be one of the next eras that you're talking about.
Yeah. Now let's spook everyone. And everyone is a little bit spooked by the rise of AI, which is itself a product of very high-performing ordinary computers. And we're ready to have a whole internet that's faked. You're saying all the nice things about where quantum computing can take us, but won't it just magnify all the bad things as well, especially AI, to the point where AI becomes our overlords?
I don't think so, because if you take a look at our most advanced...
So. No, she's not sure, just doesn't think so. Okay, go on, Michio.
If you take our most advanced military robot and put it in the forest, along with a bug, what survives? The bug finds mates, food, shelter, runs around, and does very nicely in the forest. You take a military-grade robot and put it in the forest, what does it do? Falls over and can't even get up again. When our robots become as smart as a monkey, I think we should put a chip in their brain to shut them off if they have murderous thoughts.
Get PETA in here. First the cat, now the monkeys. No animal is safe. That's a lot of faith. I will say, Neil, I share your fears. It feels like I don't trust the people who will have the power over these things. Like, sure, robot and dung beetle in the woods, bet on the dung beetle. But the human beings behind this.
The diabolical human
They're
beings.
diabolical human beings. This seems like an arm race, and it feels like we've been told this story before.
Well, there's two dangers from AI. One is immediate, one is long-term. The immediate danger from AI is automatic killing machines. What happens when drones have the permission to kill any human silhouette?
Yeah.
At that point, indiscriminately, they will just kill people because they see the silhouette of a human. That's dangerous, and that is a danger that we face today. That is drones that kill anything with a human silhouette.
Okay.
But
that's okay.
robot soldiers that can maneuver in the jungle, that outmaneuver enemy troops and stuff like that, we're like another, 100 years away from that. That's the danger of the Terminator. That is, robots that are as intelligent as humans. We're not there yet.
Wait. You yourself and I had a bet in 1999 because you were being all apocalyptic about the year 2000 and the Y2K problem with computers. Do you remember this bet? You said, like, the world was going to collapse. And I said, no, it's not. And I said, no one is going to die. And we can't count the person who dies trying to escape what they think will kill them. Okay? Like they're driving, escaping up the mountain, and they drive off the mountain. That doesn't count. So no one died. It was not a problem. But had it been a problem, getting back to your point, the failure of computer systems to control things that keep us alive would have killed billions. Doesn't that count as AI gone bad if that happens in the future, without there being a robot who thinks it's a chimp?
You mean like an accidental thing? That the computer has a malfunction?
Or on purpose?
It's like stop all heart monitors now.
Well,
No pacemaker will work.
Now.
well, robots have no purpose unless it's programmed into them.
The world has no shortage of evil people who will program into the computer something diabolical, for sure.
Well, yeah, but they could backfire. They have to be very careful that it doesn't have a blanket order to kill, including them, in which case it would be suicide.
So we got to land this plane. We've been all over the map. You're a futurist. I know this because I've been on your show. You had a radio show where all your guests were on the frontier of what was to come. Is there a sense of what is beyond the quantum computing revolution? Because philosophically, how do you get something that can do more than your single atom can do? Would that be the limit of any future tech industrial revolution that humans will ever experience? Because we've tapped out the universe.
There's one level beyond atomic, and that is nuclear. For example, MRI scans. They used to be called NMR, but people got freaked out by the N.
Yes, one of the two N words you're not supposed to use in polite company. Yeah, nuclear.
Right. Nuclear.
And, yeah.
Right. So we dropped the word nuclear and put magnetic, M, and then it became acceptable. People said, oh, just magnets, you know. But MRI machines uses the spin of the nucleus, not just the spin of the electron, but the spin of the nucleus in order to penetrate deep inside the human body. And now NMR machines save lives, thousands of lives as a consequence.
Arguably the most potent machine in the hospital for diagnosing the condition of your body without first cutting you open.
Right.
So clearly that's the case. But you're saying beyond the electron, which if it's part of an atom, there's the whole atom there. You get into the nucleus, there's another quantum revolution awaiting us if we exploit the states of the nucleus itself?
Right. That's what I'm saying. There could be a state beyond quantum computers, which are atomic. That is, they are dealing with electrons. That at the center of the atom, there's a nucleus, which is, thousands of times more massive and would allow you to penetrate even deeper
into the person's soul and then make them stop being so hateful and killing other people for stupid stuff.
By God, she's got it.
And maybe we could cure that. Maybe can it cure racism and segregation and the other supremacy I don't like talking about?
So I did not know, of course I know of atomic nuclei, I hadn't thought that the nucleus is next. And the nucleus is deep inside the atom.
That's right.
Deep in there. So
it holds it together.
It holds it all together. So then there's nothing left in the universe to exploit to our own devices.
The question that children ask is, what is the universe made of? And we still can't answer that question. We know most of it is dark energy and dark matter, but what are they?
Wait, so that elementary school, that joke that's safe for elementary school, we can't even tell that anymore? It's never trust atoms, because they make up everything. That's like safe for third graders, but so they don't make up everything. So you just ruined this joke.
That's what we're saying. Atoms are not everything.
Oh.
In fact, most of everything isn't atoms. That's the problem.
Most of everything is not atoms.
Yeah, most of everything is dark matter and dark energy, and we don't even know what that is.
So you say everything is melanated?
However it got
melanin
dark,
in
I don't know if it's melanin, but it's dark.
Okay.
Okay.
Because it's probably melanin.
I hadn't thought of it in that context.
You're welcome.
Okay. So what you're saying is the whole universe is black. That's what you want to say here.
No, I'm saying the whole universe has melanin. Everything has melanin in it if it got color, right? Unless it's see-through, correct?
Well, even that's made out of atoms. We're talking about something below atoms.
But
even
do atoms
inside-
got melanin?
Melanin is made out of atoms.
Melanin is made out of atoms?
Oh, yeah.
So dark matter?
No, we don't know what dark matter
We
is.
don't know.
Damn it, you're making me sick.
No, we got this.
All
right.
matter matters, guys. All matter
yeah.
matters. All right.
You figure it out.
We're still looking for that new particle that's made of doesn't matter, right?
What is it?
So it
Doesn't matter.
So can you then predict the end of discovery when we have complete command and control over the nuclei of atoms? And if that's the case, it kind of smells like this Kardashev scale that I've heard you...
Wait, well, who think the Kardashians got a scale now, too?
Michio, just catch us up on where we are today on the Kardashev scale.
Well, okay, Nikolai Kardashev, this great Russian astronomer, said that there are 3 types of civilizations in the universe. Type 1 is planetary. They control all planetary energies. They control earthquakes. They control volcanoes. The weather they control. That's type 1. Type 2...
That's a very powerful civilization, if you can do that.
Very powerful.
Yeah, you know, the future when we control the weather. Type 2 is a civilization that controls the sun. They mine the sun for energy. That's where energy comes from, directly from the sun. They're launching out of space, sort of like Star Trek. Star Trek would be a Type 2 civilization. Then there's Type 3. Type 3 is galactic. They roam the galactic space lanes. They play with black holes, like the Empire of The Empire Strikes Back. Now, what are we? Are we Type 1 like Buck Rogers that controls the weather? Are we Type 2 that controls the sun like Star Trek? Are we Type 3 that controls the galaxy like Star Wars? No, we are Type 0.
What? Nuh-uh. Because we use the sun. We use solar panels to get electricity.
But we don't play with the sun itself.
No, it's too big. And too high.
Yeah, I think that's the whole point. If you're a Type 2 civilization, you have overcome that restriction that the sun has
But
placed.
we use the sun. We play.
You know how much sun? We little bit of sun coming on the Earth, and sunlight is otherwise going everywhere else in the solar system, into the galaxy, and off into the
But I
universe.
play in it all
not
the time.
to be used by anybody else. But if we wrapped the sun in some absorbent material, channeled all that energy back to Earth, and had a way to get wind the sun, meddle with the reactions, change its luminosity, that we'd be a Type 2 civilization, right?
Yeah?
Okay. You're just sitting there waiting for the sunlight to reach you and using a little bit from your solar panel. That's all.
We're talking about making the sun.
Yeah. So we're Type 0. When are we going to be Type 1?
Well, according to Carl Sagan, probably in this century. He did a calculation, one of the first calculations using the Kardashev scale, and Carl Sagan said probably sometime this century we'll hit Type 1. We're very close to Type 1. We're right now 0.7.
Wait. He was not alive in this century.
Yeah, but in the last century.
So did he mean we would hit it in the last century?
Last century, right.
But we didn't.
Well, he estimated that we are a 0.7 civilization, not 1, but 0.7 in the last century.
Between 0 and 1.
Yeah.
Okay.
We're controlling the weather and making earthquakes and all that stuff.
That's right, controlling anything Earth-like, would be type 1, like Buck Rogers.
But we still run away from hurricanes and we're terrified of volcanoes.
That's why we're type 0.
Yeah, we're type 0. I don't know about that 0.7. What's going on
Also,
there?
if you get on the internet, a lot of people think we are controlling the weather.
Oh, yeah.
So there's a good part of this population that thinks we're at 1.4 right now.
If you go on the internet, you can find anything.
Exactly, yes.
So this is not a measure of objective truths of the world.
Well, I mean, it depends on who you ask.
Anyway, then the next question is, if there are other civilizations in outer space that could reach us, then what are they? Are they type 1, 2, or 3? Most scientists would say they're type 1, but that's a mistake, because type 1 civilizations can barely go to the moon. We're talking about perhaps if there are civilizations that can reach us from outer space, they're probably type 3.
If that's the case, they're coming from a galaxy we can't see because they're controlling all the energy from that galaxy.
Right, they're probably galactic. They could roam across the galaxies through wormholes, let's say. Because they can't be type 1 because they can just hop between neighboring planets. Not type 2 like Star Trek, but type 3, which is galactic. That's the energy scale necessary for them to roam across the galaxy.
Allow me to offer a cosmic perspective on all this. When I think of discovery of any kind, it's someone who's curious, who's standing on a frontier, looking out into the unknown and asking questions. And not everyone does that. That takes some deep curiosity that every child has, that somehow is beaten out of us or not nurtured by the time we're adults. Precious few adults are that curious. But those who are will peer out into the unknown and ask, what's there? How do I learn more? And there are people who say, why are you doing that? We have hungry people here on Earth now, in the here and now. In that moment, that seems like the right calculation until you realize how often those discoveries influence the state of the world years, decades in the future. Quantum physics, what decade is famous for the discoveries of quantum physics?
1925.
So a century ago, laid the groundwork for what would become the IT revolution in this world. There is no creation, storage, or retrieval of digital information without the exploitation of some quantum phenomenon. And we're on the precipice of yet another quantum leap in our advances in this field.
It's coming back.
So, if you were around back then, what would you tell the people probing atoms? You say, why are you doing that? We have hungry people in the street. Well, there's the depression. And you're a carpenter. I just care that my wood atoms cut. All right? Would you stop them because they're not doing anything that you don't think is relevant at that time? So those who do research on the frontier, they're the ones that carry civilization forward. And the degree to which that happens is a function of what is the enlightenment of an electorate, of a leadership, of a nation, of the world. And so when I look back at all these revolutions of the past, the Industrial Revolution, it's a few pages in your history book, and we take so much of that for granted. Imagine being alive then and watching it unfold in front of your very eyes. So Michio, with his book, Quantum Supremacy, he's alerting us so you don't miss it. Of course, it's going to happen to you, whether or not you happen to it. It is a pathway into the future that will transform us, I think, in our lifetimes. Is that correct, Michio? Mm-hmm. We don't have to wait a century.
Yeah, it's happening now.
In our lifetimes. I lose sleep at night wondering, with all of these discoveries, ultimately, are we actually smart enough? Are we actually smart enough to answer the questions we've posed? Or deeper still, are we smart enough as a species to even know what questions to ask? And that is a cosmic perspective. Thank you all, Beacon Theater. Thank you to my panel, Jordan Klepper, Michio Kaku, Tiffany Haddish in the house,